Okay, so last week I review about EOS, right? Okay, and actually I intend to review also the phase equilibrium, but I think we don't have enough time to cover that. Okay. It's okay. We start VLE directly. Yeah, vapor liquid equilibrium because those things I intend to review. I believe that you learn it before. Hmm. You learn it before midterm. So today we're going to talk about vapor liquid equilibrium, VLE in short. So in this chapter, we will deal with VLE at low pressure, okay, and correlating, predicting non-ideal VLE, okay. So why do we have to consider the case of low pressure first? Hmm? You know the reason? Why don't we start right away from any pressure or medium or high pressure? Why do we have to start from low pressure? Hmm? No, no idea. You see the connection of between low pressure and EOS, right? From our last week, our review on last week. No? Why? What we can expect at low pressure? Hmm? What we can expect when the pressure is low? Hmm? Pardon? Yes, and then what happened? We can have some ideal gas, right? The behavior will not much change from ideal gas behavior. Okay? And then you can approximate the fugacity becomes close to pressure. We can estimate the fugacity by using pressure. Okay, so for VLE, why do we need VLE? We need VLE because so many operation, the well, for example, distillation column or flash flash operation use VLE, right? It's fundamental. Okay. Oh, we're talking about flash operation and distillation column. So these two things are uh, separation technique. And what is the definition of separation? Hmm? What is separation? Hmm? Alan? Mm-hmm. And well, you think about distillation column, we have a mixture, liquid mixture or gas mixtures, all right? But well, in very common case, it's uh, liquid mixture. And then from liquid mixture, what is separation? We want to separate it out. And hmm, what is separation? Okay, separation. it's it's what's it? For separation, we induce new phase, okay, with different concentration, different composition. For example, we have liquid mixture with certain composition, and then you induce new phase, okay, with different composition. Then separation occur because once you induce new phase, for example, gas phase, and gas phase has different concentration, and you know that, well, once you induce new phase, you can easily separate it, right? You induce vapor phase, gas phase, and you have liquid phase. And liquid phase and gas phase has different composition, then you can separate it, right? Okay. So by definition, we can define it. I mean, separation is a action to separate a new phase with different composition. Okay. So in case of flash operation, we start from, well, feed with certain composition, and then induce, you separate the phase, right? The liquid phase has one composition, but the gas phase has different composition. Okay. So that way you can separate it out. Okay. And what happened if the new phase we created has the same composition with the other phase? For example, if while you, of course, we have liquid phase, right? And you induce new phase, but the composition still the same. Can we call it separation? No, right? Because it's different phase, but the same composition. It's not separation anymore. Okay. So so you see that in order to design and also operate the distillation column or flash operation, you need behavior of vapor liquid equilibrium. Okay. VLE. Okay. So we need data, of course. We cannot just derive from anything. We need data of VLE, vapor liquid equilibrium. Okay. And in order to obtain such data, we need experiment. Okay. You can set experiment like there's a heater and you, well, feed your mixture. For example, in this case, it's acetone and water. Okay. And set the pressure at constant pressure. Okay. And you adjust the temperature. Okay. Then you measure composition of vapor phase and liquid phase. Okay. And with this experiment, you can observe boiling point also. Okay. Okay. We call bubble point for mixture. We don't call boiling point anymore. For boiling point, well, it's used for pure phase, pure component, like in this case, acetone or water. Okay. You know, well, at 1 atm, boiling point of water is 100 degrees Celsius, and acetone is, yeah, 56 degrees Celsius. And once you change the temperature, okay, we got different composition. For example, you know, at 100 degrees Celsius, it's a boiling point of water, right? So it must be pure component, pure water. Okay. So if we write mole fraction of acetone in liquid and mole fraction of acetone in vapor, like in this table, okay, the very first line is composition of acetone must be zero, zero, okay? And the boiling point, of course, is at 100 degrees Celsius. This is a temperature at equilibrium, okay? Where we have two phase, okay? Of course, the boiling point, we have equilibrium of vapor and liquid phase, okay? And well, what about at different temperatures, like this one, 74.8, okay? And the composition of acetone must be 0.05 in liquid phase. And for vapor, well, this value, okay? Okay, it's a mixture. This temperature we call bubble point, okay? The point where, well, it's the equilibrium between vapor and liquid, okay? So at different temperature, we need different composition, of course, okay? And at the last row, okay, at 56.15, this is temperature, the boiling point of acetone, right? So if we look at the mole fraction of acetone in liquid phase, it must be 1. And in vapor phase must be 1 also, okay? And of course, if you perform more experiments, okay, more points during these two temperature, I mean boiling point of water and boiling point of acetone, you get more data, of course, okay? But this one is enough. If we plot, if we report this data, it's okay, yeah? We can see the all this data, okay? But report data in a table, you cannot see the trend, okay? How the temperature change, also how the mole fraction change, okay? So we can plot, we can present this data in different way. For example, this one, the, can you see it? The, maybe we need to turn off the light. I don't know, but okay. We plot between temperature and mole fraction of liquid phase and vapor phase, okay? Of course, one line is for vapor, one line for liquid, okay? What about the blue line? This one is trend of vapor or liquid. And what about this? Vapor, okay. So, and one thing to emphasize is, you see that this table report the only mole fraction of acetone in liquid and in vapor, okay? Because we have, our mixture is binary, binary mixture. Binary means it contains only two components, okay? Water and mixed acetone. So we don't have to report water content in vapor phase and in liquid phase, but you can calculate it, right? Okay. If you need mole fraction of acetone, no, of water in liquid, how can we do that? You subtract one, no, well, subtract this number from one, right? Okay. And also, if you need more fraction of water in vapor, of course, 1 minus this value, okay? Okay, so normally we report only the what's it, the light component. Okay, so this is mole fraction of acetone. Okay, in this graph, and we plot with temperature how it change. Okay, and the other way to present this data, we can plot between x and y. Okay, mole fraction of liquid phase and vapor phase. Okay, for this one, we have only one line actually. Okay, this line, the blue line. Okay, for the orange one, it's imaginary because this one, this line, we call it operation line. Okay, where x equal y. Okay, where the composition in liquid phase and vapor phase are equal. Okay, so why do we have to, why do we need this line when y equal x? Okay, x equal y, y equal x. So as I mentioned to you, that separation is the, what is it? You induce new phase, right? With different composition. Okay, there's one single task. And imagine that we are at one equilibrium. Okay, and we, of course, at equilibrium, vapor liquid, we induce new phase, which is a vapor phase, right? Of course, we have x and y now. X is the composition of liquid phase, and y is composition of vapor phase. And this stage, you separate vapor out, and you totally condense the vapor phase. What happened? You get liquid phase with composition of the vapor phase from the previous stage, right? Okay, so that is y equal x, right? Because you totally condense it, so the composition becomes the same, right? And then if you induce new phase again, what happened? Think about it. We start from feed, and then we fit to the first stage where composition of the liquid phase and vapor phase different, and then you separate all the vapor phase out and condense it, allow it to, what is it, separate into two different phases. And you see that the vapor phase at the first stage, the composition becomes, at the same composition of the liquid phase, right? And then you induce it again, you get new vapor phase with different composition again. And if you repeat it again and again in, a number of stages, what will happen? Your vapor phase becomes, contains higher composition of light component, right? Because you always, you induce new phase, vapor phase, which contains higher composition of light component, and then you, separate it again, right? You move to the next equilibrium point, you induce the new phase again, and it's contain higher composition of light phase, light component, right? Okay. Okay, so you now you know the reason why we need this operation line. Okay, because the composition of vapor phase and liquid phase at different, it at the, what's it, adjacent stage are equal. What about heavy component? If we want to purify the heavy component at the first stage, you remove liquid phase out because the liquid phase contain higher composition of heavy component, right? And then you flush it again, okay, at new equilibrium, okay? And of course, the composition of liquid phase is equal to vapor phase here, right? And then you flush it again and again and again, okay? So from this data, we can write this empirical relationship, okay? We write ki as a fraction of yi and xi, okay? A ratio between y and x, we call it equilibrium constant, okay? We use k, okay, which is a constant. And of course, we have two components, right? This is for one component. If we, take a ratio of light, no, more volatile, of course, is a light component with heavy component, we obtain alpha, okay? And we call alpha as relative volatility, alpha, okay? So for k is a y by x, okay? The ratio of y and x. And this one also, because it's k is y over x. This one also k, which is y over x, but different component, okay? Mm. Okay, so from the data in the table, in the previous table, in this table, we can calculate Ka and Kb, okay? Acetone and water. And we can calculate alpha, okay? At one equilibrium, we get 1K, 2K, of course. K for light component and K for heavy component. And we obtain one single alpha, okay? Now we can plot between alpha, relative volatility, and mole fraction, okay? And you see that, you notice that normally we plot against the light component, okay? Mole fraction of the light component. Yeah, it's a mole fraction of acetone. How alpha change? This is alpha, okay? K and K of stone and K of water. Mm-hmm. Okay, so what happened if alpha is equal to 1? When alpha approach 1, what does this mean? Mm-hmm. Yes, from this expression first. When alpha is 1, K of two components becomes similar, right? Okay. So what does this mean? K is a ratio between mole fraction in vapor phase and liquid phase. Okay. So once the K for light component and heavy component become closer, what does it mean? The behavior of the light component and heavy components becomes close. Okay. And once the behavior become close, it's difficult to separate, right? Okay. Okay, so at this point, we can at this point we can model the VLE, okay, vapor liquid equilibrium. Now we can model it. And what else? Of course, it's originate from data, right? We need data, and yes, from that data we can model it. Okay. However, there's no connection between thermodynamics and this expression, this model, right? What you learn in was it phase equilibrium has no connection at all with this expression, right? Because it's, well, just the data. You use the data, right? So well, what have you learned about phase equilibrium? What is the what's it? What condition? What is the condition of phase equilibrium? How can we define the equilibrium point? Hmm? At equilibrium, which thermodynamics property equals? Hmm? We have thermal equilibrium, right? We have mechanical equilibrium. We have chemical equilibrium. For thermal equilibrium, of course, which parameters at both phases are equal? Hmm? For thermal equilibrium, what is thermal equilibrium? You have two phase or multiple phase, of course, but we start from two phase. It's easier to for analysis. For thermal equilibrium, if we say that we have thermal equilibrium between these two phases, hmm? What does it mean? There are no heat transfer between two phases. Okay, no heat move across the boundary. Okay, and which parameter define that? Hmm? Temperature. Okay, and we can guarantee that no heat move across the boundary when temperature of both phases are equal. Okay, and what about mechanical equilibrium? For mechanical equilibrium, there must be no work move across the boundary. Okay, and how to guarantee that no work pressure. Pressure of both phase must be equal. Okay. But thermal equilibrium and mechanical equilibriums are not our concern here. Okay. Our concern here is chemical equilibrium. What about chemical equilibrium? Hmm? Yes, but in in broader meaning is chemical potential for both phase must be equal. Okay. Okay. So once chemical potential for both phase are equal, what does it mean? There are no change in composition anymore, right? Okay. Of course, the concentration may be different, but the chemical potential is equal. So there will no move or no transfer of any species across the phase. Okay. So in our case here, we don't have reactions. Okay. We have only diffusion or mass transport between the phase. Okay. So to guarantee that it's equilibrium, the state we consider is equilibrium. The fugacity of I component in vapor phase must be equal to fugacity of I component in liquid phase. Okay. Okay. So we divide it from fugacity. Okay. And because we are dealing with vapor and liquid, so we consider only vapor phase and liquid phase. Okay. In our current case, we're considering the acetone and water, right? So we have to consider both. I mean, fugacity of water in vapor phase must be equal fugacity of water in liquid phase. Okay. And at the same time, we need fugacity of acetone in vapor phase must be equal fugacity of acetone in liquid phase. Okay. So we have to model in order to define this equilibrium at VLE. We have to define the fugacity. We have to model the fugacity of vapor and also fugacity of liquid phase. Okay. And if we look at fugacity of vapor phase, how can we estimate the fugacity of liquid phase? Oh, no, vapor phase first. Hmm? No. Fugacity is just fugacity coefficient times with pressure. Okay. So because we consider only I component, so you need partial pressure, right? So partial pressure is YIP, okay, where P is the pressure of the system, okay. And what about YI? YI is a mole fraction of the vapor phase, right? Okay, we consider I component, so we need YI here, YIP, okay, is PI, is partial pressure of I component, okay, and we need fugacity coefficient, okay, and this one must be phi I hat, okay, because you know the difference between phi, the fugacity coefficient, and this one phi I hat. This is for mixture, okay. The I component in the mixture is not pure component, okay. Okay, hopefully you can distinguish between pure component and mixture. Okay, so but anyway, yeah, this one we need this one for frequency of the Weber phase. It's calculated, it's estimated by phi hat YIP. Okay, and remember that the very simple case we focus on low pressure. Okay, the system at low pressure. At low pressure, okay, the behavior becomes well close to ideal gas. So the Fugazi coefficient becomes 1. Okay. This is the reason why we start from low pressure. Okay. So we force the Fugazi coefficient to be 1. Okay. So on the left hand side, you get YIP. Okay. You don't, well, we can remove this Fugazi coefficient out. Okay. Now look at the liquid phase. We need Fugazi of liquid phase. And how can we calculate the Fugazi of I component of liquid phase? Hmm? Pardon? Say again. Mm, hold on. Okay. We consider the liquid phase, right? But normally the Fugazi of liquid phase is close. We can estimate it by using Fugazi of set vapor. No, not set vapor yet. Set liquid first. Okay. And Fugazi of set liquid, we can estimate it by using Fugazi of set vapor. Okay. So starting from set vapor to liquid, the Fugazi doesn't change much. Okay. So that means we can estimate the Fugazi of liquid phase by Fugazi of set vapor. Okay. And how can we calculate the set vapor? Fugazi of set vapor? Because it's a gamma I xi pi, just that. What is pi? The small p, pi. It's not the pressure of the system. It's not partial pressure of the system. This one is pressure of set vapor. Okay. And why we need set vapor? I told you just a couple of minutes ago that we need a Fugazi of set vapor, right? Mm-hmm. Okay. So the right hand side, we have gamma I, okay, which is the activity, and xi, which is the mole fraction of liquid phase, and pi, which is pressure of the set vapor. Okay. So normally we can calculate this one, pi, by using Anton equation, okay, which relate the pressure, set vapor pressure with temperature, okay. At certain temperature, we can calculate, we can estimate the pressure of set vapor of that component, okay. So for example, here we can, yeah, from that table, we use Anton equation to determine the vapor pressure, okay, of A and B, of course, and then we can calculate that gamma, okay, and the gamma we call it activity coefficient, okay. So what is the Anton equation? I will show you. Just one moment. Mm, we, where is it? Okay. Yeah. APP1. Okay. Yeah, this is Anton equation. From Anton equation, it's related to vapor pressure and temperature. Okay. There are two forms of it. The first one, but actually it's very similar. Log P is A subtract by B over T plus C, okay? Or log P equal A minus B over T minus C, okay? But you have to pay attention to the unit of pressure you obtain and also the unit of temperature, okay? Normally you need three parameter A, B, C in this Anton equation, okay? And what else? Yeah, in this is in appendix. You need, do you need this file? I can send to the line. Okay, you got the file, right? And well, I should give you this chapter also, the book. Yes, chapter 8. Okay. Oh, not this one. Where we are now? Okay, back to this. Okay, so from that data, from the data previously given in the previous page, we can calculate gamma, okay, activity coefficient at different equilibrium points, okay? And if you calculate all of them and you plot gamma and, well, you plot between gamma and mole fraction of acetone in liquid phase, you obtain this figure, okay? And it shows us how activity coefficient change, okay? And one thing to emphasize is for the pure component, what is this condition? When the mole fraction of acetone in the liquid phase becomes zero, what does it mean? Hmm? Here, what is the condition here? You see that here, well, gamma of water approach 1, right? What is the condition here? Yes, it's pure component. So remember, pure component, the gamma must be 1, okay? Activity coefficient must be 1. And what about here? This is pure acetone. And you see that gamma of acetone approach 1, okay? So for pure component, gamma must be 1, okay? Okay, so you see how it change, okay? And different components, different mixture. Of course, the trend of gamma will be different, okay? For example, if you mix water with ethanol, gamma, the trend of gamma of even water, the same component, right? Water, but water in water ethanol mixture and water ethanol acetone mixture will be different, okay? So you cannot use it, well, you cannot use the data from different mixture, okay? Even it is the same component, okay? Okay. Previously, I think you may heard about Raoult's law. This one also, we can use Raoult's law to model the VLE, right? Previously, we obtained the model YIP equal gamma I xi pi, okay? Right? We derived it previously. And once we rearrange it, yi, now yi is gamma I xi pi over p, okay? So the only problem is gamma, okay? If we assume that the activity coefficient is 1, okay, you obtain this expression, yi is xi pi over p, okay? And this is, we call it Raoult's law, okay? And it is only compatible with ideal solution, okay? Because when we assume gamma is 1, that means the mixture is behave like ideal solution, okay? We use the same ideal, but ideal solution is totally different ideal gas from ideal gas, okay? Ideal solution is, well, the component in that solution behave like they are all pure component, okay? No interaction between component, okay? That's an ideal solution, okay? And of course, if you mix ideal gas together, 2 or 3 different ideal gas together, the solution becomes, of course, it's the ideal solution because for ideal gas, there are no interaction at all, right? Okay, so it's the same, okay? This ideal solution, gamma is 1, okay? No, not this is, gamma is 1, okay? And you see that for our acetone water mixture, it's not ideal solution. right? Because gamma is far deviate from 1. Okay. So this case, acetone water is not ideal solution. It cannot be ideal solution at all because the gamma is not 1, right? Okay, so I just explained you the connection between the model we derive and Raoult's law. Okay, and if we leave the gamma I in this expression, sometimes we call this model as modified Raoult's law. Okay, or we can call it Raoult's law type activity coefficient. And now we focus on gamma. Okay, we can broadly classify the solution behavior into 4 types. Okay, the first one, when the mixture follow the ideal solution behavior. Okay, we call it type 1 solution. And for type 1 solution, look at the right, well, figure, subfigure. Okay, the upper right. Gamma for both component are 1. Okay, and for the whole range, gamma always 1. Okay, and this is the, what's it, important feature of ideal solution. Okay, gamma must be 1. Okay, and this we call it type 1 solution. Okay, so we can calculate pressure. Okay, partial pressure contribute by each component here. It's difficult to see from the screen. I don't know, maybe resolution of that, yeah, beamer is not that good because from my screen I can see clearly. Okay, all right, this line, okay, is a partial pressure of toluene. Okay, and this line is partial pressure of benzene. Okay, now example of the type 1 solution is a mixture of toluene and benzene. You know toluene, right? Hmm? Toluene. You know toluene? Okay. And benzene, you know it, right? Okay. Okay. Then so this is a contribution of partial pressure of it, right? So for total pressure of the whole system, it's just sum, is sum of partial pressure of both components. Okay. So if you look at the total pressure, of course, total pressure of the mixture must be lie between the pressure of pure component to pure component. Okay. This is a mole fraction of benzene. We plot with mole fraction of benzene, which is our light component. So this is a toluene. Okay. At this point, it's pure toluene. And this point is pure benzene. Okay. So this is a set Weber pressure of pure benzene. And here is a pure toluene. Okay. So you see that pressure of mixture lies between pressure of pure component. Okay. And now if you plot between X and Y, this graph, show X and Y. Let's see if this is better. Hmm? Okay. So we plot between X and Y. Okay. Mole fraction of benzene in liquid phase and mole fraction of benzene in vapor phase. Okay. We obtain this equilibrium line, this one. Okay. But this one is reference only. This one is reference curve. Okay. It's just Y equal X. Okay. X equal Y, right? So you see that type 1 solution always the equilibrium curve lies upper the reference curve. Okay. And it will not cross the reference curve at any point. Okay. It will not cross the reference curve. So if you consider using distillation to separate this mixture, it's very easy, right? Because I think you previously learned about it, right? You start from any a mixture with any composition, for example, here, okay? You want to separate the light component and heavy component, okay? You move this way until to reach the reference curve, okay? And then you move up, right? Go up, yeah, like that, okay? So let me draw in Zoom. Yes, yeah, right, okay? Okay, go up. You see that it's very easy to reach very pure, what is it here? Benzene, okay? And can we change the color? One moment. So I don't know how to change it. It's okay. Use the same color then. We go down the other side of the column, okay? We can easily purify it, okay? And the number of stage required, well, you can count the stage here, okay? Okay, good. Okay, so the next one, we plot between the mole fraction of benzene in liquid phase or vapor and temperature, okay? We obtain two curves. Why we obtain two curves? Because one one line we plot x, right? XA and temperature. And the other one on the same figure, we plot YA and temperature. Okay, so we got two lines. The bottom one we call bubble point, and the upper one we call dew point. Okay, bubble point curve and dew point curve. So anything, the area below the bubble point, it's a zone for liquid phase. Okay, and the area beyond the dew point curve, that is the area of vapor. Okay. Okay. If our mixture lie here, like, well, in this area, we know that our mixture must be vapor. Okay. Totally. And if our mixture like here must be liquid. Okay. And what about inside this? Inside the envelope. If our mixture lie between bubble point and dew point curve, our mixture is at equilibrium, okay, between vapor and liquid phase. It will separate into liquid phase and vapor phase. Okay, for example, if our mixture is here, the composition of our mixture is here. Well, let me draw it. Just one moment. First, I'm here. Okay, at this point. For example, we start from here. Okay, our mixture is here. This is a liquid phase, right? And then we heat it up. Okay, increase the temperature. Okay, until we reach this temperature. Oh, I should explain about this point first. Sorry. Yeah, okay. It's a liquid phase, right? We keep heating until we reach this point. What happened? We reach the bubble point curve. So we can expect our mixture start boiling, okay? And the first bubble occur, okay? At this point. This is where we call it bubble point when the first bubble occur, okay? And if we keep heat it, okay? Keep heating it until we reach this point. What happened? It will separate into two phase, liquid phase and vapor phase. Okay? And what is the composition of the vapor phase and liquid phase at this point, at this temperature? We just draw the line here. Okay? The line, horizontal line at this temperature. Okay? Because it's inside this envelope. It's separate into vapor and liquid. So the composition of liquid phase is at this point. And the composition of the vapor phase is at this point. Okay. I should also draw in the slide. Yeah. This point is composition of vapor phase. And here is the composition of liquid phase. Okay. Fahim, can you turn off your microphone? Okay. Okay, good. So the next question is, how can we estimate the amount of vapor phase and liquid phase? Okay. We use the method called liver rule. Okay. You heard about it? Liver rule. No? It's okay. One question first. At this point, what do you think? At this temperature, which one is larger? I mean, which one means, wow, which phase is larger? The amount of liquid phase or the amount of vapor phase is larger? Hmm? Pardon? The same? No, not the same. Liquid phase must be larger because the temperature just, of course, it's beyond the bubble point, but while still very far to go, right? Until it reached the totally vaporized. Okay. In order to find the amount of vapor phase, you just take this distance. Okay. This distance means, sorry, Not here. It's directly on this line, okay? And divided by the length of the whole line here, okay? And you get the amount of liquid phase. And what it's well, the amount of vapor phase. You take this distance, this length as numerator, and the whole line here, it's a denominator, okay? Okay, so let me repeat again. The amount, the fraction, I mean the fraction of liquid phase is a ratio of this length divided by the whole length here, okay? And for the vapor phase, just this length divided by the whole length here, okay? We call it lever rule. Okay, so if we keep the temperature, keep heating, okay, and the temperature keep increasing, okay, at this point, of course, it's bubble point, right? And at any point, I told you already, it's separate into set liquid and set vapor, right? With different composition depends on the temperature, right? And also now you know how to calculate the amount, I mean the fraction of liquid phase and vapor phase, right? And if we keep increase the temperature keep increasing until we reach here, okay? What does it mean here? We reach the dew point, okay? Where most of the mixture turns to vapor, okay? And beyond this point, of course, totally vaporize. Everything vaporize, okay? Becomes vapor phase. Okay? So if we start from different mixture, okay, maybe we start from vapor first. Yeah, we start from this vapor and we cool the mixture down. Okay, we still in vapor phase until we reach here. We reach the dew point, and at this point, we obtain the first drop of liquid. Right? This is dew point where the first drop condense. Okay, so you our mixture enter the vapor liquid zone. And of course, at any temperature here in this zone, it's separate into liquid and vapor, okay, with different composition. You can read the composition from this directly, okay? And if you want to find the fraction of liquid and vapor, of course, you use lever rule, the same, okay? You want to calculate the fraction of vapor, you take this length divided by the whole length, okay? Okay, keep the temperature down, decrease until we reach here. We reach the bubble point, okay? And at this point, all the mixture condensed to form liquid, okay? And down here, okay, everything becomes liquid. Okay, good. And the other things about, let me clear this first. And the other thing about this figure, the bubble point and dew point, we see that, remember that this is the Type 1. Okay. For type 1, the bubble point and dew point must be between the boiling point of pure component. Okay. Here, close to 110, it's a boiling point of toluene, right? And on the right hand side, it's a boiling point of benzene, okay? Right? At this temperature, it's 80 something. It's a boiling point of benzene, okay? And for the mixture, both boiling point and dew points are, well, lie between these two bubble points of pure components. Okay, the next one. The next one, or type 2, for type 2 solution, we call it positive deviation from ideal solution behavior. Okay. From the name, it's positive deviation. What is the meaning of positive deviation? Is deviate into positive side. Okay. And of course, it's deviate from ideal solution. So we cannot expect gamma becomes 1, right? Gamma is not 1 anymore. And it deviates. Okay. Deviate into positive side. Okay. So if we look at gamma, this is a gamma. Well, we plot between mole fraction. This example of type 2, it's a mixture of isopropanol in water, right? So you see that gamma for pure component, of course, gamma is 1, right? Gamma of water also 1, okay? But for the mixture, gamma is above 1, okay? Always greater than 1, okay? And you see that one thing is the gamma for both components are greater than 1, okay? We cannot have gamma for one component is less than 1 and the other one is greater than 1. No, impossible. Okay. I will tell you why. Okay. Why we don't have such behavior. Okay. But first thing first, why we call it positive deviation? Okay. Because once we take logarithm of 1, all these gamma, okay, are positive, right? Okay. Because it's greater than 1, then log of gamma is greater than 1. Okay. Always. Okay. And what else? Okay, so what does it mean when gamma is greater than 1? Now look at the, yes, this. Or we can look at this one, the very first, okay, expression. Gamma P, oh, YIP, sorry, YIP equals gamma I XIPI, okay? When gamma is 1, of course, what does it mean? For type 1 solution, this becomes ideal solution, right? And the fugacity, because the right hand side is the fugacity of liquid, right? The fugacity of liquid, what does it mean? It's, well, it's X, like it's behave like ideal. It's pure component, right? Okay, it's behave like pure component. Okay, no interaction at all. Okay. But what happens if gamma is greater than 1? Fugazi is greater than what should be in pure component, right? Right? If it's pure component, we have like pure component, then this is 1. Okay. But this is greater than 1, then that means, wow, the Fugazi is greater than what we expect it behave in case of pure component. Okay. So for pure component, the interaction between each molecule is the same, always the same, right? Because while let's say we have only A component in the container, in the system. Okay, the interaction between each molecule is the same, right? And also when it is in case of ideal solution, that molecule also interact with other molecule the same way it interact with itself. Okay. However, in case of type 1, this interaction is greater, and in greater in the way that increase the fugacity. So what does it mean? What type of interaction it is? Is repel each other, right? That molecule doesn't want to stay together, so it repels. Why? Why is it repels other? Because it want to increase then it increase the pressure. Okay, you can treat the fugacity the same way you treat pressure. And in order to do that, it want to be, wow, because it's repel each other. So it's trying to be away from other molecule. That way it's moved to Weber. Okay? And once it's moved to Weber, of course, the pressure of the system increase. Okay? So we can expect, for type 2, we can expect the repulsion interaction. Okay? Between molecule A and molecule B. Okay? For example, in our case, that one is water and isopropanol. Okay? It just want to stay together. It repels. Okay? Okay, so the result is increase the fugacity or increase the pressure. So if we look at the pressure, and you see that it behave like we expect. We have this is a partial pressure contributed by water, and this is a partial pressure contributed by isopropanol. And you see that if it behave like ideal solution, we should have a straight line, right? Straight line from between this point and this point. Okay. But you see that for mixture, this type 2 mixture, the total pressure is much larger. Okay. It's moved like that. Okay. And if we look at the partial pressure, also the same, right? The partial pressure is much larger than we can expect from pure component. Okay. So for type 2 solution, imagine that we have A and B, okay? And once we mix A and B together, what is it? It's against each other, okay? And so the pressure of the system increase, okay? And once the vapor pressure of the system increase, what does it mean? We can expect lower boiling point because it's easier to vaporize. Okay, we can see this graph first before we look at this XY curve. Okay. We have again we have dew point curve and also bubble point curve, the same. But you see that the we have in certain or some condition the boiling point is lower than pure component, right? Here on the left hand side, 100, it's a boiling point of pure water, and here is a boiling point of isopropanol. But for mixture, you see that bubble point is lower than, yeah, boiling point of water, and pure isopropanol. Okay. And one interesting thing is here at this point. At this point, yes, you see that bubble point cross the dew point, right? And what does it mean? Yes, we call isotrope. Mm. No, not isotrope, acetrope. Sorry, we call acetrope. And what does it mean? From this figure, the boiling point is at the same. No, the bubble point is at the same dew point, right? Yeah, that is the other things. Yes, it's true, but it's another thing. But what I want to tell you is, we only have this behavior in case of pure component, right? Normally, you see for pure component, the boiling point, dew point, we don't have boiling point, dew point. We have no, we don't have bubble point, right? And dew point, we have only boiling point, which is the same point, right? Yes, this one also, because bubble point and dew point is the same. We can call it boiling point, right? And this boiling point, we have minimum temperature, right? So we call it minimum boiling point, etc. Okay? And it's linked with the type 2 solution. Always type 2 solution, we can expect the minimum boiling point, etc. Okay? Okay? Next time when you see minimum boiling point, etc. Yes, it is type 2 solution. Okay? And what else? The other thing also the same. We have two envelope, right? On the left hand side and on the right hand side, we have vapor liquid mixture, vapor liquid mixture. Okay, but over here no, because we move from liquid to vapor phase directly without entering the vapor liquid equilibrium zone. Okay, and if we look at this figure, we plot between equilibrium curve. Okay, we plot x and y. Okay, and always we put reference curve. Okay, and we see that equilibrium curve cross the reference curve somewhere here. Okay, and this point, the point where the equilibrium curve cross the reference curve is etc. Okay, and remember that this is minimum boiling point, etc. Okay, and well, and remember that when you try to separate it using distillation column, okay, for example, we start from somewhere here, maybe, yeah. Okay, you move here, right? You stuck here. You will not get pure isopropanol. Okay, but however, if you go down, of course, you can get pure water. Okay, and if you start from a mixture above the acetrope, concentration higher than that acetrope, you can get on the right hand side on the top column, you will get pure isopropanol. Okay, but at the bottom of the column, you cannot obtain pure water. Okay, because you will stop at acetrope. Okay, and if you look at the, because the equilibrium curve cross the reference curve, and you know reference curve is x equal y, right? Y equal x or x equal y. What does it mean? At acetrope, the composition of liquid phase equal the composition of vapor phase. Okay, get it right? So at acetrope, y equal x. Okay, we see it from here. It's y equal x. And well, I will tell you why we cannot separate it across this acetrope. Remember that for distillation column, we start from any mixture and then we induce vapor phase, right? And we need that at that equilibrium, the composition of x and y must be different, right? So you can separate it, and that because you obtain different composition, and then you move it to different equilibrium, and then you can separate it, right? However, at this point, once you reach the acetrope point, what happens if you induce new phase? Hmm? You obtain vapor phase and liquid phase, but the composition is the same. Yes, and even you take the vapor phase, you still have the same composition. You try to condense it, and then you induce new phase, new vapor phase, but the composition still the same. Okay, even you induce new phase, but the composition doesn't change, so you cannot separate it. Okay, so if you start from the composition below the acetrope, you must find the way to cross the acetrope point without using VLE. Okay, because by using VLE, you stuck here, you stuck at the acetrope. Okay, anything else about type 2? No? We can break for just 10 minutes, okay? Yes, my microphone is off because we are, wow, we are during break. Okay, we break for 10 minutes. Okay, you can hear me, right? We break.
ได้ยินค่ะอาจารย์
Ani, Ani Latif asked me again about, yeah, my microphone is off. Maybe he missed something. Yeah, we during break. We just start now. Just resume now, okay? So, okay. So, any questions regarding the type two type two solution? No? Okay, it's clear enough. The next one is type three. For type three, we call it negative deviation from ideal solution behavior. It's okay. It's type three. So it's opposite to type two, actually. And we use the word negative deviation. That means it deviates to negative side. Okay. So we can expect that gamma must be lower than one, smaller than one. Okay. So gamma is smaller than one. Okay. You see for the whole range, except pure component. For pure component, of course, we have gamma equal one. Okay. Gamma equals one, and then gamma lower than one for the whole range. Okay. It's well, a mixture of acetone and chloroform in this case. So while previously about type 2 solution, we have interaction between molecules that, well, when when the molecule repel each other, okay, between A and B, okay. But this one we have an attractive force, okay, between A and B, right? Because once gamma is lower than one, what we can expect, okay, we can expect smaller fugacity, right? Okay, it's smaller than in case of ideal solution, right? So fugacity is lower, then wow, of course, pressure must be smaller than what can it could be in case of pure component. Okay, so for the whole range, gamma is lower than one. Okay. Oh, and previously I told you that we cannot have a mixture where gamma for one component is greater than one and the other component is smaller than one, right? Why? Because you see that physical meaning of it, when in case of type 2, we have what's it, repulsion between A and B. That means, well, if A doesn't like B, B also doesn't like B, A, okay? Okay? And in this case also, if A attract to B, B also attract to B to A, okay? Also, if we look at the partial pressure, okay, the partial pressure in both cases is smaller than ideal behavior, okay? Contribution by pure component, okay? So the total pressure is smaller than pure component than set vapor of pure acetone and chloroform, okay? Then we can expect the rising of bubble point, right? Okay, this is bubble point. On the right hand side, we have boiling point, right, of a stone. And on the left hand side, it's a boiling point of chloroform, okay? But in case of mixture, the bubble point deviates. Okay, and we have a very high boiling point here. Okay, at the middle. Okay, in between, and this point, of course, it's boiling point because dew point and bubble point is at the same point, right? We don't have envelope of vapor liquid equilibrium here. And again, this point is acetrope. Okay, but in this case, it's a maximum boiling point acetrope. Okay, it's opposite to type 2. It's a maximum boiling point. Mhm. Okay, we have minimum boiling point acetrope. Now maximum boiling point acetrope. Okay, and we have to separate vapor liquids mixture envelope. Okay, now we look at the here on the left hand side. The the we plot between equilibrium curve and reference curve, and we see that equilibrium curve cross the reference curve somewhere. Okay, and that point, the crossing point, is called acetrope. Okay, and here again, if we start from the mixture with composition smaller, lower than the acetrope, and we separate it using distillation column, of course, at the bottom, we obtain here, right? Pure component. However, at the other side, we obtain acetrope instead. Okay. Any questions? If not, we can move to the next one. Yes. The yes, the maximum boiling point. Hmm? Yes, we call this type is maximum boiling point acetrope. The one, yeah, no, it's the same point. Okay, this is acetrope. You see, the composition is the same composition. Hmm. Yeah, somewhere here. Okay, so type 4. Type 4, it's actually it's a type 2 with strong interaction. You remember type 2, right? Type 2 when we have gamma greater than 1, right? Okay, where molecule repel each other. And for type 4, if that repulsion force is stronger, well, it's separate. It will not move to just vaporize easier, but it will form another phase. So this type, we have vapor, liquid equilibrium. We have two liquid phase. Okay, this one is, what is it? Butanol, right? And butanol and water. It should be water, right? Pure water. And butanol and water. Okay, and you see that gamma is greater than 1, of course. Yes, and we have certain range when from this range, in this range, okay, we have two liquid phase. Okay, in this range we have two liquid phase. So that's why we have gamma more than one gamma. Okay, there's gamma for phase one and gamma for phase two. Okay, in this range because we have two phase, two liquid phase. Okay, and because it's it's like it's like type 2 with stronger interaction, so we can expect that the pressure, the total pressure of the mixture is greater than pure component. Okay, mm. Okay, we have equilibrium curve and we have reference curve, right? The same. And well, the equilibrium curve cross the reference curve here, okay, somewhere. And so we have azeotrope again, but in this case, the azeotrope occur in the range where we have two liquid phase, okay? Because in this zone, we have two liquid phase, right? Okay, so over here, we have azeotrope. And you see that if we look at bubble point curve and dew point curve here, we have azeotrope here, right? And at this azeotrope, we have two liquid phase. Okay, so for type 4, we can call it heteroazeotrope. Okay, we learn four types. Okay, the first one, what is the first one? Ideal solution. Type 2, it's a positive deviation. And type 3 is negative deviation, right? And the last one is heteroazeotrope. Okay, and what about also, well, remember that for azeotrope, the one condition applied for azeotrope is mole fraction of vapor phase must be equal to mole fraction of liquid phase. Okay, y equal x. Okay, at azeotrope. Okay, we still well consider the VLE, vapor liquid equilibrium model of vapor liquid equilibrium. We start from empirical, right? Where k is y over x, right? And we define alpha, which is relative volatility. And then we derive the, what's it, Raoult's law type. And Raoult's law type with activity coefficient, where YIP equal gamma I xi pi, right? The question is, what happens if one of your component cannot be condensed at that pressure, at the pressure of the mixture? For example, uh, water and ethanol, everything is okay, right? Because ethanol can be condensed, right? Water can be condensed. Then you can find PI, set Weber pressure, right? However, if we consider water and oxygen, it's a mixture, of course. Water, this oxygen dissolved in water, and it can form Weber liquid equilibrium, right? You have Weber phase contain oxygen, and also you have liquid phase, water and oxygen, something like that. But the problem is we cannot model that way because we don't know set Weber of oxygen. Yes or no? So how can we solve this problem? Using Henry law, right? The very simplest way to solve the problem is we cannot find the set Weber of oxygen, right? No problem. We assume it to be constant. And we call it Henry law. Henry law constant. Okay, Henry's law constant, HI. And this constant, Henry's law constant for different species, of course, must be different. Okay. And we can determine it using experiment. Okay, this type. And you see that it's exactly the same. We have YIP, right? On the left hand side. And on the right hand side is XI, HI. Okay? Instead of gamma I, XI, HI, because gamma and PI can be combined, right? To HI. Okay. Now you learn about VLE. We go while we going to apply it. For flash calculation, assume that we fit one stream, okay, to the flash drum, okay, with steady flow, steady state flow, and then it's flash inside this drum, okay, flash to Weber and liquid. And from material balance, assume that well, this Weber, the flow of Weber is V, and the flow of liquid is L, right? So from material balance, we can write F equal V plus L. Okay. Okay. And if we look at each species, for example, component I, well, assume the composition, the mole fraction of the component I is Zi, okay, in the feed. And we have Yi and Xi, okay? So F Zi, F Zi equal Vyi plus Lxi. Okay, this is the balance for species I. Okay, and remember that we can relate between Yi and Xi, right? Using empirical one, like Ki is Y over X, Yi over Xi, right? This way, or we can write using this VLE. Yi over Xi is gamma I Pi over P. Okay. Okay. The next one is how can we find the gamma? Okay. What about PI? PI we know Onton equation. If you know temperature, then you can calculate PI, right? But what about gamma? Okay. For gamma I, we need activity coefficient model. For example, this Fala equation where we can write log gamma A as a constant A xb square over AOB XA plus XB total and square of this term. Okay. But this is not the only way to model gamma. Okay. There's a bunch of methods find the gamma. Okay. And in the next chapter, we're going to discuss about how can we model the activity coefficient. Okay. So by using this material balance and material balance for species I and this VLE, we can solve this problem. Okay, so beside that flash drum, we have 4 cases of VLE calculation. The first type of problem is bubble point calculation. Okay, so for bubble point calculation, we assume that L, I mean liquid phase, is equal F, and there's no V, okay, from that system. Okay, in short, you have liquid phase, okay, and people ask you the bubble point of that mixture, okay, our mixture from start from liquid phase, okay, and you know we need more information. The first information is temperature specified bubble point, okay, where temperature is given and also composition of the liquid phase is given, okay. So we know the composition of liquid phase, okay, and we know the temperature at the equilibrium, okay, and you must calculate the pressure and composition of the vapor phase at that equilibrium, okay. So from given temperature, then you can calculate set vapor, right, of PA and PB, okay, by using Anton equation, okay, and from given XA, we know XB, right? How to calculate XB is a 1 minus XA, right? Okay, then you can calculate gamma A and gamma B because always the model of gamma A and gamma B relate is a function of X. You see, it's a function of X. For example, in Valor equation, is a function of X. Gamma is a function of X. Okay, then you can calculate gamma, right? Gamma A, gamma B, okay, using Valor equation. Okay, so in order to solve this problem, you try P, okay, at no variable, okay, and then you calculate YA and YB and check if summation of YI is equal 1 or not, okay. If the summation of, well, mole fraction of vapor phase equal 1, and then you stop, okay. This one is the simplest case, okay, because here in our VLE, Pi is a function of, it's an Anton equation, right? So it's a function of temperature, okay, and P are given with temperature, so we can calculate P directly, okay. And the other thing is X, the mole fraction of liquid phase is given, okay, XA is XB, then you can directly calculate gamma A, okay. So that is the reason why I said it's the simplest case. The next one, we're going to calculate the bubble point again. But we are given with pressure P and XA. Okay, the composition of that liquid phase. Okay, so we know the mole fraction of liquid phase, and then from the mole fraction of liquid phase, you can calculate gamma. Okay, gamma A, gamma B. Okay, by using one line equation. Okay. However, we don't know PA and PB. The sat Weber pressure, saturated Weber pressure, we don't know, and we cannot calculate it directly. Why? Because the Armstrong equation is a function of temperature, right? This, we don't have information of temperature, right? We're going to find temperature. Okay, so we cannot write PA as a explicit function of temperature. Sorry, we cannot write temperature as a explicit function of pressure. Okay, because it's another way around. Okay, it's the other way around. Okay, so we have the function of PA as a, we can write PA as a function of temperature. Okay, but we don't know temperature. Okay, so we have to plug that in. So from given P and no variable from here, we know XA, XB. Okay, then you have to calculate YA and YB by using, yeah, equation 8, this one, and check if summation of yi is 1 or not. If not, you try out T again. You change the temperature again. And with the temperature you change, you calculate PA and PB, right? And with PA, PB, you can try again, find YA and YB, and check if summation of Y is 1 or not. If not, you adjust the temperature again. Okay. Hmm? Yes, I know. So you try out T. You guess T. Trial is guess, right? You guess T and then you calculate PA and PB. Okay, back to the first type, bubble pie calculation. This one is the simplest one. T is given, then you can calculate PAPB directly. XA, XB, we know, okay? Because we know we start from liquid phase. We know the composition of liquid phase. Then we can calculate gamma, okay? It's very simple, right? To calculate P and YA, YB, okay? However, this one, P is given, and we know XA, XB because we start from liquid phase. We don't know T. That is our problem because we know XA, XB, we can calculate gamma, but we cannot calculate PA, PB, okay? So we have to guess temperature first. And then from the guess temperature, we obtain PA, PB, okay? But it's not the real one, it's a guess one, okay? Then from that PAPB, you calculate YA, YB and test it. Okay. If summation of YI equal 1, then okay, you stop. If not, go back to this stage. Try out T again. Okay. You guess new T. Okay. And then calculate PAPB and then, well, finally check summation of Y. Okay, the next one is dew point calculation. For dew point calculation, there's two types. The first one is temperature specifying dew point. Okay. And the next one is pressure specifying. Which one is easier? Temperature specifying, right? Because when we know temperature, we can calculate PAPB directly. Yes. If we are given with P, with unknown T, you have to guess for T. Okay. But even this one is hard enough because we calculate dew point. That means we start from Weber mixture in a Weber phase. Okay. We know YA, YB. We are given with YA, YB. We don't know XA, XB. And the problem is gamma is a function of XA, XB. If you don't know XA, XB, you don't know gamma. Okay. So to solve this problem, okay, we given with T, then we can calculate PAPB, right, using Anton equation. Then you have to guess XA, XB. And from the guess value of XA, XB, you calculate gamma A, gamma B using one line equation. Okay. And then try out for P and no variable from previous step. Okay. And using PLE to check XA, XB if summation of X equal 1 or not. If not, guess new XA, XB. Okay. When you guess XA, XB, that means you guess only XA, right? Because XB is 1 minus XA, always. Don't guess both XA and XB. Okay, so what else? Hmm? Yeah, summation. Yes. Okay, yeah. From this one, you can start from, I don't know, maybe approximate. The gamma is 1, and then you obtain some value, and then you can use those obtained value as a guess XA, XB. Okay. Okay. What about this one? This one is the most complicated one. Well, we calculate dew point. We are given with pressure, okay, and composition of vapor. Okay. We have composition of vapor because we start from vapor phase. A mixture with vapor phase. Okay. With known composition of vapor phase. Okay. But we are given with pressure. That means, well, we don't know temperature. Okay. So we have to try guess T first. Okay. And then you calculate PA and PB. Okay. Using Anton equation. Also, you guess gamma A, gamma B. Okay. And then calculate XA, XB by using Butler equation. Okay. And from, oh, sorry. it must be the other way around. You guess XA, XB, and then you calculate gamma A, gamma B. Sorry. Using one line equation. And from given pressure and YA, YB, and also, well, X, gamma A, gamma B. Okay. We check, we calculate it and check if summation of X is 1 or not. If not, yeah, repeat the step. Okay. Trial T again. Guess new XA, XB. Okay. They are more complicated calculation. This is a isothermal flash calculation. Okay. When temperature and pressure specified. Okay. Okay. From here, assume that, well, we have relation between YA, YB, X, Y and X, right? From our VLE, okay? Or empirical, it's all right. Then we have material balance, okay? And we have species balance for component I, okay? Then you can write that this way and YA, YB, okay? So in this case, we can calculate from this procedure given PT. So that the composition of the feed, okay? And the last one is a diabetic flash calculation. For a diabetic flash calculation, we have a mixture, okay? And then you feed that mixture to flash drum, okay? And what's it? We don't know temperature and pressure yet, okay? But we know that that flash is a diabetic flash, okay? So no Q, no heat transfer, okay? So the feed must be in two phase, okay? And that from that two phase, you separate vapor and liquid out. Okay. For this adiabatic flash calculation, you need not only mass balance, you also need the heat balance, enthalpy balance. Okay. Okay. The next one is traditional K factor method. This is also empirical. Okay. This method, it's relate Y and X. Okay. Using this empirical model. Okay. Ki is Yi over Xi. Okay. And of course, we assume that Ki depends on pressure and temperature. Okay. But we need the chart like this. We call it the Priester K factor chart. So on the top of the chart, you have pressure, okay, scale of pressure. And at the bottom, you have temperature. Okay. So as I mentioned to you that we assume that K depends on pressure and temperature. Okay. So if you know pressure and temperature at that equilibrium, you draw a line between temperature, you specify temperature and pressure, okay? And see if your mixture contains methane, okay? And you see how the line draw between pressure and temperature cross each line here, okay? And you read the value in this scale, okay? You can find the Ki, okay? Then you can relate between Y and X, okay? But if you don't know, you are not given with pressure or temperature, you are asked to determine the temperature. At which temperature you have to guess temperature. For example, now we're going to estimate the bubble point, the bubble point temperature at 200 psia and the dew point composition of liquid mixture of 1.29 mole percent of methane. This is the the composition of your mixture given, okay? And you must use the Priester K-factor chart. Okay. The problem is we know the pressure, right? But we don't know the temperature. So we cannot draw a line between pressure and temperature, right? So what to do? To solve the problem, you try temperature, yes? You guess temperature, yes? And then with that guess temperature, you draw a line from that temperature to pressure, okay? And read K for methane, K for ethane, and K for propane, okay? And then start calculate it, okay? Okay? With given P and trial T, draw a straight line across the Priester K-factor chart. And then you read K value at crossing point of your component. And with given Xi and Ki, you read from the chart, okay? You check if summation of Y equal 1 or not, okay? If it's not correct, then you adjust your temperature again and then find new K, all right? Mhm. Okay, any questions? Hmm? How to read? You see the number here? For example, if the no, not this one. Uh, Okay, if the line cross, yeah, I don't know, it's not line anymore. Okay, it's cross here, right? You read it, 9 something. This is 9, 7, 8, 9, 10, right? It's close to 10. It's 9 something. ใช่ครับใช่ถ้าไม่รู้เป็นอ่านเป็นค่า K ของ component นั้นอือฮึโอเคแล้วในโจทย์เมื่อกี้คือไม่รู้ทีก็ต้องสุ่มทีขึ้นมาอืม จนกว่า summit ซัมของ y เท่ากับ1 okay okay so next application of Raoult's law, it's of course we can, beside VLE, we can apply this type of Raoult's law in non-volatile solute. For example, in boiling point elevation. Okay, you know, well, in a mixture, of course, from pure component, you for example, you have water, right? You add sugar, and you see that the boiling point will elevate. Okay, so you can calculate the elevation of boiling point, okay, by using this type of expression. It's Kb times with molality of solute, okay, and of course you need database on Kb, okay, and find the concentration in terms of molality of the solute of the sugar you add to water, okay, and this one you can, with this expression, you can determine the elevation of boiling point, okay? And in order to determine the boiling point, of course, you need boiling point of pure component plus the boiling point elevation, okay? For example, for water at 1 atmosphere, 1 atm, the molar boiling point elevation constant is 0.51, okay? So when you dissolve sugar in water with dilute composition, the solution will boil at, yes, this one. If you dissolve 1 molar, right? Molality of solute, 1 molar of sugar, okay? And also freezing point depression. The freezing point also depressed, okay, by introducing solute, okay? You introduce sugar into water, okay? We can determine the freezing point depression based on Kf time molality of solute, okay? And Kf is, you have to check the Kf, okay? Okay, Kf is here, right? Minus 1.86, okay. Okay, so let us conclude for today's lecture. Well, the first one is observation of liquid phase activity coefficient. We have 4 types, right, of mixture of solution. The type 1 is ideal solution, where gamma is 1, right, for both components. And for type 2 and type 4, of course, gamma is greater than 1. And the difference between type 2 and type 4 is type 2, it's, we have VLE, right? But type 4 is heterogeneous. We have hetero. And for type 3, the gamma is less than 1, okay? And type 4 behavior is an extreme example of type 2, actually. Yes. The activity coefficient are larger than for type 2, but have the same general shape, right? Yes. For type 4. Okay. We will deal with this later. Okay. Next week. Okay. So today we just learned about VLE. Okay. How to model VLE and also calculate bubble point and dew point. And in case of bubble point, you have, well, two types of calculation. For bubble point, of course, we start from liquid phase. Then, because we start from liquid phase, we know the composition of our mixture. Okay. And most of the time, you are asked to determine the bubble point at certain pressure or at certain temperature. Okay. So if temperature is given, of course, they will not ask you about temperature. They will ask you about pressure, right? And if temperature is given, you can directly calculate the set Weber pressure. Okay. And with that set Weber pressure, well, you can calculate PA, PB, and also gamma because you know XA, XB already. Okay. And with VLE model, you can calculate YA, YB, and pressure. Okay. If not, you're given with P and you are asked to calculate temperature instead. With that one, it's more complicated because without P, we cannot calculate PA, PB. Okay. So we have to guess temperature first in order to find PA and PB using Armstrong equation. And then from XA, XB, you know, gamma A, gamma B, right? You use VLE model. And with your guess value of temperature and PA, PB you obtain from that guess value, you check if summation of Y is 1 or not. If not, you change temperature again and then, yes, calculate. And for dew point calculation, you start from mixture in vapor phase, okay? And you are given with composition of that vapor phase, okay? If you know T, of course, you can calculate PA, PB, right? And you follow the same, yeah, similar, not the same, similar, yes. And if, well, you're given with P without T, that's your problem because P, you cannot directly calculate the PAPB, right? You have to try T also, right? And for gamma, you don't know gamma A, gamma B because you don't know XA, XB. You are asked to determine XA, XB. Okay? So read the PDF file I gave you. It's a book. Okay? And at the end of that book, that chapter, I give you only one chapter of it related to this. You will find the problem, some problem. Okay. Please be sure that you can calculate bubble point calculation and dew point calculation with different types. Okay. Okay. So we finished today.